In this question, we have triangle DEF, and we know that it has two equal sides. So at least two equal sides, and those sides are equal to 3. Which of the following taken alone would be sufficient in finding the area of DEF? It's important that taking these alone, so don't try to combine information from more than one of these. So what we have here, looking just at A, is the ratio of DE to EF is 1 to the square root of 2. Now obviously we just want to jump in here and say, oh, I got it. 1 times 1 to the square root of 2, which means a 45, 45, 90 triangle. And indeed, that could very well, pardon the drawing, but that could very well be a possible triangle that adheres to those constraints. The question, though, is it the only possible triangle? Because if the answer is no, there's another possible triangle, then we wouldn't be able to find the area of DEF, because there would be another triangle with different dimensions and therefore a different area. The question, of course, is what would those dimensions be? Well, notice, and this is the tricky part, is if we had, instead of 1 square root of 2, we just had 1 square root of 2 square root of 2. Now, first you're saying, wait a second, didn't it have to equal 3? But this is only a ratio here. So before, it actually equaled 3 root 2. Now, the square roots of 2 are the ones that correspond to the 3. So they would be sides 3, and then this would be 3 over the square root of 2. You don't actually have to know that exact measurement, but you can just see that, oh, we would have a different triangle. Again, both sides equal 3. And this equals 3 over root 2 here. But the ratio is as follows. Therefore, different triangle, different dimension, different area. A is not sufficient in of itself. Let's look at B. The sum of angles DEF and EFD are 135. So if you have a 45, 45, 90, of course, same thing again. You want to say, oh, that this is 90 and this is 45. Those are the two kind of angles represented here. The thing is, though, we could also have another triangle where you have these two angles, and they are equal to 67.5 and 67.5. And this angle up here would be equal to 35. Totally different looking triangle. Therefore, this alone would not be sufficient to find the area of the triangle. So finally, that leaves us with C. The sum of angles DEF and FDE is 90 degrees. That means what about the third angle? Well, it must equal 90 degrees. Notice that these triangles, there was no angle that equaled 90 degrees. And here, when we have an angle that equals 90 degrees, it can't be the side that corresponds to the 3. That means the other side would also have a 90-degree angle, which is already 180 degrees. Therefore, the two equal sides must be here and here, meaning that we have the 45, 45, 90. So therefore, C is the answer because it's the only one where we only have the 45, 45, 90 and not some other possible triangle.
In the diagram above, AB equals BC and AC equals DC equals DB, what is the measure in degrees of angle DAC? Well, this is an awfully tricky one because we have these two equations. What we're going to do is get rid of everything except the equations and make the diagram a little bit bigger. So first of all, let's think about AB equals BC. This big side equals this big side. And so the big triangle, ABC, is an isosceles triangle. So I'm just going to call this X, the two base angles here Y, and then this whole thing, that whole thing is Y. And we know that, of course, X plus Y equals 180 degrees, but we don't know the value of X and Y right now. So we can't do much more with that. But that's the big triangle. Now I'm just going to say, let's look at this piece here. AC equals DC. Well, that means that what we have here is an isosceles triangle also. And we have a base angle of Y, so the other base angle must be equal. That must be an angle of Y. And we see we have an isosceles triangle with two base angles of Y. It has to be similar to the big triangle. And so this has to be X right here. Okay, so the little triangle DAC is similar to the big triangle CAB. So we have Y, Y, and X. And again, X plus Y equals 180. We can't solve for anything else. But now if we look at this piece here, DC equals DB, we have another isosceles triangle here, a big obtuse isosceles triangle. The base angles here, one is here up at angle B, the other one is here, and so that has to be X. All right, well, now it gets interesting, because now if we look at what's going on at vertex C altogether is y, but it's also two angles equal to x. So it's x and x. So in other words, y equals x plus x, or y equals 2x. Well, that simplifies things amazingly, because now we can come to this equation and plug that in. We get x plus 2x plus 2x equals 180, or 5x equals 180. Divide by 5, x equals 36, y is 2 times that, so y is 72 degrees. And so we have, in the big triangle, we have a 36-degree angle at the top, and then 2 base angles, each of 72 degrees. And the question is asking for this angle, DAC, so that angle there has a measure of 72 degrees.
So the first thing to note in this problem is that if this angle was 90 degrees, which is not the case here, in that case we know the area would be, this is our altitude, that's the base, would be 20. And that corresponds to that column B. Now, of course, the condition is that the area is less than 20, and we have to compare the measure of this angle to 90 degrees. So really, I'm just going to tweak this triangle relative to this right triangle. So imagine I'm going to rotate this arm DE like that. This length is still 5, so the point E goes here. Now this is my new triangle, and the area here, the base is still 8, and the altitude here, this would be now less than 5. So it's a number less than 5. And that certainly satisfies the condition that the area of this triangle EDF is less than 20. But here, the measure of this angle EDF is greater than 90 degrees. Now we look at the other way is I'm going to rotate in this direction, the same arm, that DE. So this length is 5. Now here, the altitude again would be less than 5, because if you notice in this right triangle, that's the hypotenuse, so this side has to be less than the hypotenuse. So again, I can make the angle less than 90 degrees and still end up with a triangle that has an area that's less than 20. So it's possible for the angle to exceed 90 degrees, and it's possible for it to be less than 90 degrees, which means that the relationship cannot be determined. We don't have enough information. The answer is D.
Okay, let's begin by sketching our two known sides. We have a side of length 8 and a side of length 6. Notice that the location of these two sides dictate the location of our third side, since the third side must join the ends of our existing two sides. Now we'll be finding areas of triangles here, so we'll need this formula. For all of our triangles, we're going to keep 8 as our base. So as you can see, the area of each triangle will depend exclusively on the height of each triangle. For this question, we're going to find the complete range of possible areas, from the minimum possible area all the way to the maximum possible area. Let's begin with minimum possible area. To minimize our area, we need to minimize the height of our triangle. So just how short can we make our triangle? Well, let's see. By bringing this red side down closer to the base, we can make our height quite short. In fact, we can make that height as close to 0 as we want. So from this, we can determine that we can make our area as close to 0 as we want, as long as it's greater than 0. What about the maximum possible area? Well, to maximize the area, we need to maximize the height of our triangle. So let's bring our red side up, and we can see that the height of our triangle is maximized when this angle is 90. The area of this triangle is equal to 1/2 times 8 times 6, which is 24. So we know the range of our possible areas now. The area must be greater than 0 and less than or equal to 24. So as we can see here, all 3 of our possible areas work. So our answer is E. To begin, we should recognize that the question sets up a few restrictions for our diagram. To begin, these two angles must be 90 degrees, and the lengths of AD and DC must be 6. Now, given these restrictions, it's quite possible that ABCD is a square, in which case all four sides would have length 6. Under this scenario, column A would equal column B. However, we can create different shapes that still adhere to these restrictions. For example, our shape could look like this, in which case AB is longer than BC. In other words, column A would be greater than column B. So as you can see here, our answer must be D.